So what I want to talk about today is really about a specific area of programmable infrastructure and how programmable infrastructure is going to change the way we build clouds. But I had to come up with a better title than that. And so I came up with this idea of calling it Always in the Kitchen at Parties. And I feel I should explain that. This is a reference to a somewhat obscure sort of synth pop hit from the early 1980s. So kind of only people of my era will maybe recognize that song. It was a medium hit. But the inspiration for using that as my reference was actually watching a presentation by Guido Appenzeller from Intel, also one of my former colleagues at VMware. And Guido was announcing these new infrastructure processing units that Intel has recently launched. And he made this interesting analogy about the way, in your house, your kitchen and your living room and your dining room might all be quite close together, and people flow quite easily between them. Whereas in a hotel, the kitchen's quite well separated because you want to keep the guests out of the kitchen. And so I thought about that as an analogy. And I think, the Always in the Kitchen at Parties reference is like, well, you actually would like your guests to stay out of the kitchen, even in your own house sometimes. And I also thought probably there are a lot of computer scientists like me who have been at parties and found themselves feeling a bit awkward and just ended up in the kitchen because that's where all the food was. So those are kind of the reasons why I picked this title. But trust me, it's going to have something to do with P4, and it's got a lot to do with programmable infrastructure. Now, anybody who's seen me give a talk before will probably know that I like to talk a little bit about the history of networking because I have the advantage of having been involved in some of that history and haven't forgotten everything that I did over the last 30 plus years. And so while today's talk is really about programmable infrastructure and the future, I do want to talk a little bit about some of the history of programmable infrastructure, and in particular, the rise of smart NICs. And I recently read an article that sort of pinned the invention of the smart NIC to somewhere around, I think, 2015. And that sort of triggered a series of thoughts for me about what I was doing in my very first job right after finishing my PhD in 1988. I went to the University of Edinburgh, by the way, so my PhD's from Europe. And then after that, I moved off to New Jersey and I went to work for Bellcore. And as you'll hear in a moment, I ended up kind of accidentally landing in this space of building high-speed network interfaces, or what we thought were high-speed at the time. And as I would view it now, what we actually built were these things that could reasonably be called smart NICs. So I'll talk a little bit about that history. But really the interesting thing about all that was, we've got a very long history of identifying particular functions that might be better done outside of our main server infrastructure. So, modern data centers are racks and racks of servers, but increasingly we're finding there's a lot of other things in a data center that are doing interesting work beyond the servers. Now, of course, the switches would be one example of that, but there's a lot of other things. And this idea of smart NICs and infrastructure processing units and data processing units, these are all classes of what I would call interesting, specialized hardware that's starting to change the way we think about the allocation of functions within a cloud. So this is roughly the timeline that I'm going to walk through. And as I said, you'll just have to trust me that I'll eventually say something that's relevant to P4. So this is the history part of the talk. So early in my time at Bellcore, I got involved in these things called Gigabit network testbeds. And these officially kicked off in 1989, so very early in my career. And I was involved in the one up on the right-hand side of this picture called Aurora, which linked together Bellcore in New Jersey, IBM Research in New York State, MIT in Cambridge, Massachusetts, and the University of Pennsylvania in Philadelphia. So we had a fairly large network that we were setting out to build to interconnect all these research institutions. And the thing that was really crazy about the Gigabit network testbeds was that the backbone of the internet at this point in time was 1.5 megabits. So we were talking about a 3 order of magnitude step up in the amount of bandwidth that we were trying to move through these wide area networks. And even Ethernet at the time, 10 megabits was state of the art. So even 2 orders of magnitude faster than that. And so we had a lot of ideas about optical fibers and packet switching and how to make these gigabit networks. But there was a thing which kind of turned out to be a bit of an afterthought, which is if you're going to build a gigabit network, you should probably be able to run some applications across the network. And that probably means you should be able to connect some computers to it. And in the end, this whole question of how do you connect a computer to a very, very high-speed network for its time, that turned out to be a really hard problem. And in fact, in the final report that came out of the gigabit networking testbeds, host I/O turned out to be one of the most challenging areas. That is to say, it was this problem of how do I get packets out of the host into the network? As I say, it was kind of an afterthought, but it turned out to be really hard. So what we started doing in the early days of these gigabit testbeds was building SmartNICs. Here's an excerpt of a paper that I published a couple of years in, where I was describing an early architecture for what would reasonably be called a SmartNIC. And probably the key things here is that I identified this bottleneck of where the host connects to the network. And just in case you're thinking that I claim to have invented this, I absolutely did not. Here's a paper from 3 years earlier by David Cheriton and his student Hemant Kanakia, where they also were building high-speed networks, and they also identified that they needed to start rethinking how do you get packets quickly in and out of a host. And they identified that the current state of the art wasn't going to get us there. And I think the architecture that they built was not 100 miles different from what I ended up building. So this idea was kind of in the water in the late 80s that we needed to rethink how we connected computers to networks. Now, you could reasonably say, both of these quotes highlight the fact that we needed to do something that was fast, but did we actually need something smart? Well, here's the thing that I actually built. And this is a picture done with, state-of-the-art 1980s LaTeX, in which I've shown the rough architecture of the hardware. And it's actually not that different from a SmartNIC of today. There's a couple of Intel CPUs. We used the best and fastest Intel CPUs that we could fit onto a reasonable piece of real estate. They were from what was those days called the toaster division of Intel, where they built embedded processors. And there was some specialized hardware for doing optical transmission and putting packets into sonnet frames. We didn't really know any better way to put packets onto optics in those days. We, of course, had an FPGA because what you can't do in a general purpose CPU, maybe you could do it in an FPGA, and we had the biggest, hottest, and most expensive FPGAs we could put our hands on. And then the sort of general purpose control registers for communicating with the host. Now, this does not look 100 miles away from what you would think of as a SmartNIC. It's got some general purpose CPU, it's got some programmable logic, and it's got some dedicated hardware for talking to the link layer. Why did we build it this way? Well, the short answer is because we didn't know what we were doing. And this is a normal mode of operation for researchers. You want to have enough flexibility to be able to try out things without actually knowing what the future holds. And at this particular point in time, we really didn't know what the future was going to be like, particularly in things like transport protocols. There was a real belief at this point in time that TCP and IP might be fundamentally too slow and complicated to operate in gigabit networks. There was the concerns about how expensive it was to process TCP and IP packets in software, and how would it work if you had a bandwidth delay product going up by 3 orders of magnitude with these high-speed links. So there was real interest in doing things like experimenting with new transport protocols. And then on top of that, there was the sense of if the transport protocol was really expensive, then maybe you couldn't afford to do it in the host, but rather you should offload it to the NIC. So we kind of thought we'd be doing transport protocol experimentation and transport protocol offloads. And in the end, that wasn't exactly what proved to be the most useful. We did actually offload all of the ATM related stuff. And, ATM's a bit of a packet switching footnote these days, but we had to deal with the fact that we were sending little packets and the host did not want to be interrupted every time a little packet arrived. So we had to do segmentation and reassembly. And then all of the really nitty gritty packet processing stuff around formatting and parsing headers and checksumming them and all that sort of thing. Now, but remember those because you'll find that this comes up again and again. Well, this is what sorts of things you can offload on a modern smart NIC. And I'm not going to go over this entire eye chart, but this is from a few years ago. I grabbed this from the Mellanox blog, and they've done a whole lot of offloading onto their NICs, and that they categorize NICs as being foundational, which is to say not very smart, intelligent, which is somewhat smart, and then truly smart. And depending on how smart your NIC is, you can offload more and more stuff. And so without going into the details here, clearly the idea of offloading functions from your host to your NIC has just grown and grown over the sort of 30 years since I first was working on that, and Cheriton and his team were working on it back in even earlier. Okay, so I want to talk about why you should and perhaps why you should not offload things from a server. So this is kind of a cautionary tale, and this comes from my experience of working with Ben and other folks at Nicira. So I joined Nicira in 2012, and Nicira at that point had just shipped the first version of their network virtualization platform. And one of the problems that the team had run into was that the NICs of 2012 did a really good job of offloading a certain set of TCP functions. So the very idea that we had back in 1990 that offloading a bunch of TCP functions might prove to be worthwhile had actually taken hold. And it was almost exactly the same things that I was doing, except I did it for the ATM layer. The NICs of 2012 did it for the TCP layer. They did header parsing, they did checksumming, they did segmentation and reassembly. And that was actually the really big benefit, was that instead of sending one TCP segment at a time between the host and the NIC, you could line up these giant buffers and just tell the NIC, here's the buffer, go send it, and it would do all the segmentation for you. And then in the other direction, it would reassemble everything for you. There was only one thing wrong with these NICs, which was that they were so wedded to the idea that the only protocol that mattered was TCP IP, that the slightest change to the encapsulation caused them to lose all of their performance. And so what we found was that as soon as we turned on any kind of tunneling, we would see a massive drop in performance, to the point where many people just said, tunneling just doesn't work. And from our perspective, as people trying to innovate in the space of network virtualization, this was kind of a deal breaker, because we had to be able to tunnel. We had to be able to put an outer header on top of our packets so that we could virtualize the network. So tunneling was fundamental to what we wanted to do. And we fundamentally couldn't do it at speed with the NICs of 2012. Well, one of our colleagues there, Jesse Gross, came up with this incredibly brilliant hack called STT. And STT was a way of encapsulating packets that put an outer header on top of the packet you were trying to encapsulate it, and did it in such a way that it completely persuaded the NIC that it was still doing TCP. Now, I won't go into the details of STT, but I'll say it was such a brilliant hack. It worked perfectly. However, when we took it to the IETF and we said, well, look, here's a thing that's in production, they said, that may well be, but you may not publish this as an RFC. It is too dangerous. So we said, okay, fine, we'll just keep running it in production and not publish it. But eventually, we actually came up with another set of encapsulations. First, there was VXLAN, and I'm sure you're all familiar with that. And the interesting footnote from my perspective is that VXLAN, in some respects, was actually a worse encapsulation than STT, which is to say it had less flexibility. And again, we were in the space where we were trying to innovate. We had to be able to flexibly change what went on in the packet so that we could add new features to our network virtualization platform. Just like me back in 1988, we didn't know what we were doing. I mean, we had some ideas, but we were still innovating. We were still experimenting. We had to try new things, and that meant we needed flexibility. And so this is what the Genève packet header looks like. And I feel like you can't really do a networking talk without at least one packet header. So this is the one for today. And I just want to point out the only really interesting thing on this slide is the fact that Genève has variable length options. And so what that means is we gave ourselves a place to do experiments, to innovate, to try new things. And this was really fundamental to what we were trying to do in the early days of network virtualization. But of course, hardware people would look at that and say, you can't put variable length fields into a packet. How would we ever parse such a thing? And so we had quite lengthy debates with NIC vendors and chip vendors and operating system vendors. And eventually we got everybody to agree that perhaps we could survive with some variable length options with a way of punting if you didn't know what to do with an option. So we enabled some innovation. And of course, you can maybe begin to see how this is becoming relevant to the world of P4 and programmable hardware, because this kind of view of the world where hardware can only do the one stupid thing you told it to do when you made the ASIC, that is the world that we're moving away from now, as hardware, even very specialized hardware for doing switching and NIC functions, as that becomes more programmable, we can have things that are more flexible, which lets us do more in the way of innovation. So we've now got a whole lot of opportunity to do offloads. And one of the things that happened a lot, and I think Ben may remember this as well from our time at Nicira and at VMware, was everybody who was building SmartNICs wanted to come and talk to us about moving Open vSwitch onto the NIC. And for most of the time that we worked on this, we couldn't quite persuade ourselves that this was a good idea. You can go and read Ben's paper, which I've referenced at the bottom here, which talks a little bit about this. But the thing was that if you wanted to offload OVS and get a real benefit, you had to offload it 100% of the time. And if there was some subset of special cases that could not be handled by the offload engine, then you were going to process them through the slow path or through the software path, at which point the additional cost of a very expensive NIC had not really bought you all that much, and you just ended up with a more complex system. And so we generally felt it wasn't time to move OVS to an outboard offload engine. To make it even less compelling, the performance of OVS got really, really good. It wasn't always good, but the OVS team did a phenomenal job of making OVS performance amazing on the x86 server. And so it wasn't often the case that we were that terribly worried about the performance to the extent that we wanted to offload it. You could find some cases where the latency was a matter of some concern. And in those cases, typically telco workloads, for example, or high performance computing, you could probably start making the case for offloading OVS. But again, the key to being able to do things successfully when you don't exactly know what you're doing is to be flexible. And that means programmability. And that was one of the huge benefits of OVS, was we could change the functionality of the switch every day if we wanted to. And so this idea of programmability being critical to innovation and critical to success was really quite central to this whole discussion. So if you wanted to take away kind of one point from this whole thing, it's if you're going to offload, do it very flexibly or have a really good understanding of what it is you're offloading. Well, speaking of offloading complicated things, these days, of course, people are talking about offloading the hypervisor to the NIC. And the first time I heard about this was during a VMworld. I think it was about 2019. So prior to that, there'd been this long-running sort of skunkworks project at VMware to get the VMware hypervisor ESXi to run on the ARM architecture. And so in 2018, when people showed up at VMworld, they found Raspberry Pis sitting under their chairs with a little piece of SD card with ESXi loaded onto it. And so all of a sudden, people were running ESXi on Raspberry Pis. And, is it useful? I don't know. Is it cool? Absolutely. And so a year later at VMworld, the only way to sort of outdo that was to take advantage of the fact that a lot of SmartNICs have ARM processors on them. And so the demo in the keynote at VMworld 2019 was ESXi running on a SmartNIC. Now, when I saw this, I thought, well, just because you can do something doesn't mean you should do it. So, I really hope this turns out to be a useful idea. But, actually what happened the next year was VMware announced Project Monterey. And then I started to appreciate why this was a good idea. Because once you start offloading the hypervisor to the NIC, it's not really about changing the performance profile. It's about changing the control point. And I'm going to come back to this point. But what's happening now, if you look at what's going on in that picture on the right, is there are a whole lot of things that happen as part of the hypervisor. It's not just compute virtualization, it's storage virtualization, it's network virtualization, it's security services, and it's allocating resources among different VMs so that you can basically compose different pieces of infrastructure with the right amount of compute, the right amount of network, the right amount of storage to do a particular job. And so moving your control point off to a dedicated outboard processing engine gives you this new control point. Now your guest can do different things. So as in the example that's shown on this slide, you no longer need to run a hypervisor at all on the guest. You could simply run a bare metal Linux, on top of which you might run Kubernetes, or you might run another hypervisor there. So you've now created new opportunities to do different things in the guest because you moved all of those functions that do resource allocation, network virtualization, storage virtualization into a different spot. And this is basically what we're beginning to see with things like AWS Nitro. And to be clear, I'm showing this in non-chronological order because AWS Nitro has been around longer than the stuff I just showed you from VMware. AWS, Amazon Web Services, have been offloading things onto specialized hardware for quite a number of years. This particular picture that I gathered from the All Things Distributed blog is from 2017, but they'd been doing it for a few years before that. So the interesting thing that's going on here is the top picture is a very conventional view of how you use a hypervisor within a cloud. You've got customer stuff, the guests that runs on the top of the hypervisor. The hypervisor is there to allocate CPU resources to different customer instances. And then there's networking functions and storage functions and management security functions, all of which also run on that same server infrastructure. And the observation that's made by Werner Vogel is 30% of your CPU cycles that could have been spent looking after customers are now being spent actually doing sort of administrative tasks like carving up the resources. And so what Amazon concluded quite a while ago was they should start offloading those things and having these dedicated Nitro offload engines, which some of which came from the Annapurna Labs acquisition. And so they've got a collection of different specialized offload engines that let them do network virtualization, storage virtualization, security services, management, all outside of the hosts. And the hosts are now almost 100% dedicated to the client or the guest or customer. Now, there's quite a few interesting things going on here. One is I've annotated this bottom picture to show that the hypervisor running on that server now is actually optional. You could have a hypervisor there, or you don't have to have one. You could just give the entire bare metal instance to the customer and say, knock yourself out, run on that, whatever you want. Or the customer might be another service that then installs its own provisioning system, like VMware runs a service where they put their hypervisor on the AWS bare metal and then serve up those instances to their customers. So there's lots of different things that you can do now that you've moved all of the thing that used to be in the guest onto this more dedicated hardware. And so the point I'm starting to develop here is this is a pretty complicated business. It's not just about things go faster. It's that you actually change the playing field in terms of what gets done where and what's possible. And you can kind of see, these are a quick summary of the claims that are made in this same blog post of all the good things that Amazon claims happen when they do this kind of offloading. Now, if I'm truly honest with myself, I'll say not all of these are obviously true, but it's pretty clear that you've stopped spending cycles in the server on all of these sort of overhead functions, and you're now spending those cycles somewhere else. So is that actually better performance? Well, I don't know. It looks better for the guest, but I've just moved the function from one place to another, and I've spent some money to get that new hardware. So is it lower cost? I don't know. Depends on how much that specialized hardware cost. But what you can do in this environment is you are actually now able to change the way you allocate resources to customers. You can give them 100% of the server if they want it. And that is actually quite a significant thing. The other thing is you've kind of changed the security layout, because there's now a piece of infrastructure that is completely owned by the cloud provider. That's the stuff at the bottom. And then there's a piece of infrastructure that is completely owned by the guest. And there's no overlap in the code between those two. So if you compare the bottom picture against the top picture, you can kind of see in the top picture how, a malicious cloud provider could probably use the hypervisor to inspect what's going on in the customer instance, and how you could build a system using the bottom architecture where that's not possible. Now, is it better? Your mileage may vary, but I think there is at least a different architecture here. It's effectively an air gap between the code that's run by the cloud provider and the code that's run by the guest. And that certainly gives you a different perspective on where your security boundaries are. Amazon claims faster innovation, and I think that's probably a pretty legitimate claim. An example that I just used was running VMware Cloud on top of AWS kind of really benefited from this architecture. And then they claim formal verification. And again, I don't know why that follows, but I tip my hat to anybody who formally verifies their hardware. By the way, that's what my PhD thesis was on in 1988. So tip of the hat for formal verification. And the other observation I want to make here is what's going on in this picture does not actually have that much to do with hypervisors. I mean, they're all over the picture, but a hypervisor is actually not quite the right tool for what AWS does. Hypervisors are really clever things. They let you pick up a workload and move it from one server to another. They let you do load balancing. They let you abstract away the changes of hardware from one generation of server to another. But actually, AWS doesn't need most of that. What they need is a way to allocate resources to customers and let the customers do whatever they want with those resources. And so they used a hypervisor because it was the tool they had. But they're very upfront saying it wasn't really the perfect tool. And what they've done with Nitro is build something that is now more along the lines of, we've built a specialized set of hardware to do the job we actually need to do, which is allocate resources to customers. And I talked to somebody at VMware about the Project Monterey that I showed earlier, and it's a similar philosophy that by moving all of these functions out to a NIC, you've now effectively got a programmable cable that lets you connect pieces of infrastructure together and build a sort of composed service. And this is really powerful. You can have a little bit of compute from here, a little bit of storage from here, a bit of network from there. And now you've got a different way of putting resources together for customers, as opposed to the old way of, I'm just going to carve out pieces from a single x86 box. All right, well, I can't do a talk about P4 without mentioning this man, the patron saint of P4, Nick McEwen, and I couldn't resist the chance to make a joke about him being a different kind of smart Nick. And the reason I bring him up at this point is because not only he's the guy who's been sort of inspirational both in software-defined networking and in a lot of the work that went into P4 and programmable switching hardware, but he's also a person who is really good at explaining exactly what he's doing. And I have really benefited from having Nick explain to me how P4 changes the landscape and how programmable switching hardware changes the landscape. And Nick has often used this analogy of it being the thing that switching needed that graphics already had, that there were these GPUs that evolved over many years to become extremely programmable, and they were really well optimized for a whole set of tasks, and not limited to just graphics, but things like doing crypto mining, for better or worse. But we got this whole new class of infrastructure that was very programmable and very, very different from x86. And effectively, P4 has done this again, but with a view to doing it in a way that's optimized for switching. Or I should even say more broadly, not just switching, but networking. And, I feel like this slide is a really important one that shows the difference between your truly general purpose processor, which is to say something, a high performance x86 device, and an actual programmable chip. So on the left, I'm showing you a graph from a pretty recent Intel performance report on how good they've managed to get packet forwarding on x86. So this is a single high performance x86 core, can now do about 75 million packets per second and 40 gigabits in round numbers for those tiny packets. So that is really, really impressive to do that on a single core. And it's that kind of performance that made it feasible for us to run Open vSwitch on a handful of cores in a server. But compare that against a proper programmable switching chip like the current generation of Tofino. That is a switching chip that does programmable switching at 25.6 terabits. So that is roughly, 3 orders of magnitude more than a single x86 core. Or in other words, you'd need almost 1,000 cores to get close to a single Tofino chip. So that's the amazing thing about programmable infrastructure, is the fact that when you do it right, you can get this blazing performance, but also get generality. And that is really the big takeaway in this whole talk, if there is one, is yes, you want high performance, but you have to not sacrifice generality to get it. And so here's the latest entry, which happens to come out of Nick McEwen's team at Intel, with the P4 packet processing pipeline right in the middle there. So it's got programmable hardware, and it's got a whole bunch of more general purpose ARM cores up on the top right. And this is the latest generation of infrastructure processing unit. And it was this announcement that Guido was talking about, which inspired me to talk about always being in the kitchen at parties. And what you're seeing here is a piece of hardware that is focused on providing the right kind of offload engine for the modern cloud. So it's designed to let you offload storage virtualization, network virtualization, resource allocation, management, cryptographic functions, security functions, all the kinds of things that we've seen people offloading, whether it's AWS Nitro or VMware's Project Monterey. And the launch of this particular chip was done in conjunction with Google, who of course also has a big cloud and is also very interested in how do you efficiently run your cloud infrastructure. Now, just a quick diversion here. I've spent a fair bit of time trying to understand what's the difference between an IPU and a DPU. So data processing units are the term used by some parts of the industry. I think Pensando and NVIDIA, Mellanox also use the term DPU, whereas Intel uses IPU. I haven't yet found a really significant difference between them. And I did lots of research on this. I'm sure somebody from Intel or one of the other companies I mentioned will tell me I've got it wrong. But to back me up, I went to this very helpful website called servethehome.com. They have a lot of information about these IPUs, DPUs, and the broader SmartNIC universe. So I kind of adapted this spectrum from their reporting, and it just shows a spectrum going from very, very dumb to very, very smart, with NICs with offloads being the first step up, and then smart NICs the next step up, and IPUs, DPUs the next step. And then they put this kind of exotic category at the end, which is things like FPGA based IPUs and DPUs. And what you see as you go to the right is you're getting more flexibility, more generality, potentially more cost because it's a more complex device. So what do we get from having all of these IPUs and DPUs and smart NICs? Well, hopefully, if you've been able to pick up anything from the talk so far, this is not just about performance. Yes, you're picking up a function and moving it from one place to another, but that's not a guaranteed way to make things go faster. In fact, in some cases, it will make things go slower. And I did a blog post about this a few weeks ago, and both Guido and Nick reached out to me to tell me I got it wrong, which is very kind of them. They did it very politely. And they kind of both pointed out that my blog post was perhaps a little bit too focused on the performance side of the equation. And so what I want to stress today is it's more than just performance, and I'm going to send a copy of this talk to Nick and Guido and see if they appreciate it. It's really about a bigger set of things. It's like separation, moving the functions that guests care about into the servers, moving the functions that the cloud providers care about into dedicated hardware that the cloud provider owns. So you've got x86 or ARM as the things that run guest workloads, and then infrastructure processing or data processing for the things that the cloud providers are in control of. And that is resource allocation, isolation, composing infrastructure, networking and storage, virtualization. All of those things are the job of the cloud provider. The guest just wants to run their workloads. So you separate them out into things that are optimized for doing those jobs. And the thing which I find really interesting about the current generation of IPU is how many things are sitting in that chip to make it optimal for the task, right? It's not just a whole collection of ARM cores. It's not just a P4 chip. It's not just a crypto accelerator. It's a really general purpose collection of things, some of which are really good at doing programmable packet processing, some of which are good at doing other functions. And so, this is a complex space, and that's why we have the sort of proliferation of interest in building these quite sophisticated devices to be the new programmable infrastructure for enabling innovation in the cloud. I've talked a little bit about the security piece of this. I don't claim to be a security expert, but I think there's at least an intuitive appeal to the fact that the guest code runs on infrastructure that is dedicated to guests, and the code that runs the infrastructure runs on things that are dedicated to the infrastructure. That feels like a good architecture. And it's really flexible. So, again, as I said earlier, this IPU or a smart NIC or a DPU, it's basically like a programmable cabling machine. You can connect server cores up to storage devices, up to network appliances, and you can do it in a way that doesn't just require you to carve up a single server. You can pull things from the other side of the data center and connect them in through this programmable cabling infrastructure. And so I think that's really cool. And in fact, Guido pointed out an interesting thing to me. The infrastructure that you connect up to your IPU that runs guest workloads doesn't have to be x86 or ARM. It could be a GPU. You could have something that's not at all like a traditional server and connect that up to your IPU and still have the ability to provision it, to manage it, to provide tenant isolation and all those kind of things. So effectively what we've got here is the ability to make a new set of trade-offs. Instead of just saying everything runs on the server, and if it runs on the server, that's going to cost us, now we've got a different way to sort of slice up the capabilities and get the performance cost benefit that we want. All right, so here's my forward-looking part of the talk. Here's what I think the data center of the future is going to look like. There are going to be lots of servers. I think we could be pretty sure of that. There'll be a mixture of x86 and ARM. Will there ever be a different kind of architecture? I'm not going to guess. But there'll be a lot of other things. There will definitely be GPUs and TPUs and probably other versions of those. There will be programmable switches. Hey, let's hear it for P4 and programmable switches. There'll also be fixed function switches, but for reasons that I've touched on today, there's an awful lot of value in having the programmable switches in the modern data center because of the way it lets you innovate with things that you haven't already tried out. I think there'll be quantum computing. I've done a set of other talks on quantum computing, not for today, but quantum computers are starting to show up as cloud services. I'm pretty sure that you could go and rent time on a quantum computer from IBM and Amazon already, probably the other cloud providers too. So, in at least some data centers, there'll be the chance to go and run your code on a quantum computer. It'll probably be accessed much the way you access a GPU today. And then there'll be smart NICs and there'll be IPUs and DPUs. And, I think there's such obvious value now that, Amazon has obviously bet very heavily on this. Intel's betting on it, Google's betting on it. And, it's not just the big companies are voting with their feet and their dollars. I think the arguments that I've been able to pull out from studying this for a year or so really do start to add up because of all the benefits. It's about much more than just performance. And so that brings me to my final slide, which is a picture of an elephant. So why do I have a picture of an elephant? Well, you've probably heard the story about what happens when 4 blind men grab hold of an elephant from different angles, and they all have a different opinion about what they're holding on to. So I feel like that's actually the way these IPUs and DPUs are shaking out. So, my first attempt to explain them, I was kind of saying, oh, it's kind of a nice performance optimization. And then I, had my view corrected by people who are a bit closer to the field than me. And so I think the value really depends on who's looking. And by the way, like the marketing from everybody in this space absolutely sells the performance benefits, but I think it's a lot more than performance. I think it's about security, it's about flexibility, it's about control, it's about innovation. There's a lot of things going on here. It's not just, oh, it runs faster. Now, I think I can now say, having looked at offloads for over 30 years, there's always going to be trade-offs. If you want the simplest, cheapest thing, just go with fixed function. If you want to be able to do things that you haven't quite figured out yet, you're going to want more flexibility. And, if you look at what is going on in modern clouds, that trade-off really seems to be swinging now in favor of let's go with the flexibility. And, finally, I think we're at a really exciting time, and this community, the P4 community, is very well positioned to be part of what's going on here, because programmable switching and the P4 language or whatever other languages we come up with to program those programmable switches, it's changed the playing field. It's made this idea of programmable high performance infrastructure very much more viable. And I guess what I find really cool about this story is, it's not the first time that I've heard about using P4 for something other than a switch. I think I may have talked about it with Nick McEwen 3 or 4 years ago, but it's now really seeming to get serious traction. That this idea that programmable hardware gives you a new way of building things that let you get both flexibility and performance. It's not just switching, it is actually changing the way we build the entire architecture of the cloud. And I think that's pretty cool. So I hope that folks have found this a worthwhile discussion, and it's a good way to get you fired up to go and dig in on P4 for the rest of the day. That actually is the end of my formal presentation. I'm just going to throw this up so that you have a chance to figure out where to read more of the stuff that I'm working on. This could loosely be described as an advertisement, except that we do everything for free. So if you want to read more of the stuff that I'm working on, it's all on these different URLs. We do use GitHub for building books, and so feel free to check us out there. And I think that this is now a good point for me to take some questions. And I think I see one already.
Yeah. So what if I try to sort of read the questions into the stream so that it reads a little bit more like a discussion?
That would be beautiful.
So Bruce, we have a question from Ed Nutting. So Ed asks, are we reaching a point where post-quantum crypto in the public cloud is something we should be concerned about as consumers of cloud tech? Or do we still have time to resolve the hardware requirements? Will it change the architecture of these systems at all?
Yeah, so this is a pet subject of mine, actually. So I actually am really interested in this kind of post-quantum crypto. We don't know when current cryptography is going to break, but the likelihood that it will break is getting higher and higher. I think you'd be a very bold person right now to bet against quantum computing breaking most current crypto. Is it 5 years' time? I'd say that's probably too aggressive. Is it 10 years' time? Maybe. Is it less than 20 years? Well, I'd say pretty likely. One thing to think about is if you are a dedicated attacker, you might just start grabbing data today on the hope that you'll be able to decrypt it in 20 years. And so I think this is the stuff we have to be thinking about is there are candidates for post-quantum cryptography. So I think it really all comes down to your sort of tolerance for risk. I think the big bug that came out over the weekend, the logging the logging bug, it's probably a much bigger deal than when crypto gets broken by quantum computers. But the fact is that RSA is at risk, and so I think you've got to assume that like the first people who have cryptographic the ability to break crypto using quantum computers are probably not going to tell the world about it. So that, this is I've seen somebody said in the chat about NIST expecting it around 2030. That feels like a good guess. But so I do think it's something that we should be thinking about, crypto agility, and it's going to be something that if you have the chance to start planning for it, you should. But it's actually quite difficult. And I think, we're going to see a lot of people running around trying to change how they do logging in the next few weeks. Think about trying to change how you do crypto. It's probably quite a lot harder.
That's a really complete answer. I didn't realize that quantum computing was an interest of yours. So while we're waiting for another question, one of the books of yours that I want to point out to everybody here is the book on 5G. One of the other organizers, Shabazz, pointed me to it, and I read through it. It's not a long book; you can read through it in a long afternoon, but it explains all the crazy acronyms that 5G has, and you'll come away from it with a much better understanding of how these things go together.
Yeah, thanks for the plug. And that's I'm not a co-author of that one, but I'm a big fan of that book. The acronyms of 5G are a bit of a nightmare. So, and again, if people want to find that book, it's easy to get there from the URLs. Looks like we do have another question coming in.
Yeah, we do. So this question comes to us from Ankit Gar, and he asks, how do you see the IPU or DPU tying in with decomposable infrastructure, or rather composable infrastructure?
Yeah, I mean, I think this is exactly why it's a thing that makes a lot of sense, for example, for VMware to be involved in. So I was trying to make this point about how an IPU or DPU can be thought of as like a programmable cable. So if you think about how do you connect your server today up to a storage array? Well, you run a storage network between the server and the storage array. How do you connect up to the other network? You have another network interface for that. What you'd really like is to have one interface that sits on PCI that you can program, like how much networking does it do, how much storage does it do, and what's it pulling in from other parts of the data center to connect up with some x86 or ARM compute. So I actually think this is where the IPU DPU thing is going, is instead of pulling storage or networking resources out of the server where the compute is, you'll pull them from somewhere else in the data center. And so this idea that you can compose things out of these bigger, more flexible pools of different kinds of infrastructure, I think that's exactly what the IPUs and DPUs enable.
Bruce,
you're great at summarizing, Ben.
Trying to summarize your answers, and please step in if I
no, if only I could be so concise.
So we do have another question. So this one is from David de Andres Hernandez, who asks, what would be the strategy for handling lifecycle management of both the servers and the SmartNICs when they take up such a critical role?
Yeah, that's a good one. So I don't think I have enough insight into that. I mean, it's such a new field, but I think, one way to think of it is they're going to be just a new class of infrastructure that, you'll cycle through them the same way you cycle through generations of x86, and they will have firmware and software upgrades that you'll have to cycle through the same way you cycle through hypervisor upgrades. And so my sort of naive answer here would be, it's going to be pretty much like managing your x86 server infrastructure. There is going to be lifecycle management, which, as we know, is a pretty important part of operating these kind of clouds. And, to the extent that it's possible, those things have to be automated. But to my way of thinking, it's not radically different than the situation that we're in today.
That's great. So wow, the questions keep coming in, which is great. So Ed Nutting says, related to David's question, which was the one that we just talked about with lifecycle management, related to that, we've seen recent mishaps at Google, Facebook, and others causing networking outages affecting billions of users. How do we make sure these programmable networks are stable and better protected from such human errors?
Yeah. So, I mean, I think, again, if there was an easy answer to that, it would be already figured out. But I think the one area that I feel there's a huge sort of disparity between networking and the rest of infrastructure is we don't use automated test enough for networking, automated test, automated verification. And so, I've written a little bit about this idea that if you're going to say, if you take an extreme example, if you're going to build a chip, before that chip gets fabricated, there is a massive amount of verification that goes on because it is so expensive to have a chip go into fabrication with an error. And so, there's huge amounts of software tooling going back 30 years have gone into verifying chip designs. That same idea is now increasingly applied to verifying the correctness of software systems, which is why I kind of liked the formal verification claim of the AWS Nitro team. We're kind of rubbish when it comes to verifying network behavior. Like, we push out changes to our network configuration, and then somebody says, "Oh, shouldn't have done that. Let's roll it back." And I feel like, compared to how we roll out new application versions, we're less good at testing, verifying, having good rollback plans, A/B testing, all that kind of stuff. So my kind of, sort of slightly provocative answer here, I think, is we need to adopt more of the best practices from other fields of computer science to be better at not rolling out network functions that aren't properly verified.
That's great. I also would like to see more verification in networking and throughout sort of the field of computer science. It's not an area I know nearly enough about to be able to contribute to it. It seems like you have a history in it going back a long time.
Well, I certainly spent 3 years of my formative years working on verification of hardware. And I'm never going to get those years back. But I more recently started paying attention to network verification because I've been working a bit with the team at IntentionNet, which is one of the companies that does network verification. And they have a tool called Batfish. And like one of the things I've learned from talking to that team is the set of people who are sophisticated enough to use Batfish is pretty small. It's a little bit of the experience we had at Nicira, where the set of people who were sophisticated enough to do network virtualization in 2012 was pretty small. Thankfully, over time, we managed to sort of lower the barrier to entry, and it became more and more mainstream. So I think that's where we are with network verification. Is sophisticated people do it today, but it should become more mainstream.
So there's a follow-up on this from Ed Nutting, who points out that we verify chips and they don't change very, very quickly or until we apply many millions of dollars to them. On the other hand, software networks change a lot faster. He says, do you think that boils down to needing more engineers to tackle the scale?
I mean, I think it's a combination of things. We need good tools, and there are some tools out there. We need people who know how to use those tools, but we need a culture where people don't expect to configure networks at 2:00 in the morning through the CLI. Right? I mean, I think that is one of the things which has been bothersome to me, is the kind of the failure of the networking community to move forward into a more modern way of thinking about things.
That's great. So our session here is scheduled to finish up in only about 2 minutes, which means that we'll be moving on to our next session, which is a coffee break. So you are unfortunately expected to provide your own coffee at this conference. Bruce, I know that you're in Australia, and it's so there's very good coffee there. I think it's the wrong time of day for it, though.
Yeah, but there's also good beer, so I can probably manage to make it work.
Oh, that's great. I want to say thank you so much for coming and giving such an inspiring talk. Do you have any parting words as we finish this write up?
Uh, I think I'd just say thanks to everybody for taking part in this. I see we had about 50 people on today, which is great, and I really enjoyed a chance to interact with people. This, these virtual conferences aren't always as much fun in terms of interaction, but this has been really great. I appreciate it, particularly all the questions.
Well, I love how it's possible and practical for 3 continents worth of people to join together right here.
Yeah, fantastic.
So thanks again, and I think you're probably going to sleep soon, and I hope that I am too.
Yeah, well, you really pulled the short straw. So thanks, Ben, for staying up late in California.